Okay, so the conversion of alkene diol is made possible by osmium tetroxide. So if we look at the structure of that, we can see we have this osmium metal center, and it's surrounded by 4 oxygen atoms which it's double bonded to. And then we have our model alkene. So what happens here is, these oxygens are electrophilic, as we've said before. So the osmium draws some electron density away from the oxygens, and so they want to somehow get some more electron density. If they were to bond with the carbon, that would provide them with more electron density. So they act as our electrophiles. Our alkene acts as our nucleophile. So we form this carbon-oxygen bond. We then break one of these carbon osmium bonds, and we also can form a second oxygen carbon bond. So what that gives us is this osmium in the middle again. We've formed 2 bonds to the carbon. So when we perform this reaction in the presence of water, that provides us with an opportunity to then hydrolyze the osmate ester to give us our diol. So if we go back to the species that we had at the end of the first part of the reaction, okay, so we've had our osmium structure, and then in this case, when we add some water to it, the water acts as a nucleophile. Okay, so the lone pair of electrons here will react with the osmium, and then that allows the osmium oxygen to leave. Okay, same thing can happen here. Okay, and then we can end up with we could end up with these negatively charged oxygens, but in reality, when the osmium tetroxide reacts, we would end up with some protons floating around in solution, and that is what gives us our our diols. Okay, and then we end up with OS structure. And the one thing we then need to just remember is the first part of this reaction happened concertedly. All of the bonds were made and broken at the same time. So once again, much like with making the epoxide, if we have some stereochemical information to start with, that stereochemistry will remain. So in this case, both R groups are on the same side of the alkene double bond, and so both of them would end up still being on the same side, and that will carry through into the product. So we end up with this stereochemical product at the end of it. And what that means is that this reaction, and much like with the epoxide reaction, these are stereo specific. Okay, so the actual mechanism itself leads to a stereochemical outcome. It's a bit like when you did the SN1 and SN2 reactions. So with the SN1 reaction, because you form the carbocation, the stereochemical information that started with is lost. The SN2 reaction, because all the bonds were made and broken at the same time, the stereochemistry that was in the starting material is carried forward into the product. In the SN2 case, it's inversion. In this case, we have some stereochemical information. We have a cis or a trans alkene, and that cis or trans alkene will carry through into the product because all the bonds are made and broken at the same time. There's no opportunity for bond rotation, and because of the way the mechanism works, the reaction with that alkene has to happen from one face of the alkene to give us our product. So that is stereospecific. The starting material stereochemistry dictates, because of the mechanism, the product stereochemistry. If, as in the case of the SN1 example, you form a carbocation, for example, at that point you could get different kinds of attack, and so that would then be a stereoselective reaction. So just after this this bit of the course, just going to check that you understand those definitions of stereospecific and stereoselective.